Um, I'm sure many of you have seen this slide before. We're going to be focusing now on this part down here in the corner. Now, CEMAS is known as the Center for Electron Microscopy and Analysis, and we're going to be focusing on the analysis part of the title now. So we will be looking at X-ray diffraction here. Just a little bit about myself. I was born in the UK, grew up near Pittsburgh. I got my undergraduate degree at Drexel and my graduate work at Cornell. From Cornell, I went to Xerox for 5 years, where I did both transmission electron microscopy and scanning Auger microscopy, surface analysis. From Xerox, I came to OSU and helped start the campus electron optics facility. So I was there as an assistant director from 1982 through 2012, when the CEOF was morphed and became CEMAS, as it is now. While I was at the CEOF, I looked after mostly TEM, but I also did SEM, looked after the Auger system there. I looked after the first FIBs that we had, and then also inherited the X-ray diffractometer. So I've basically bounced around a lot of different techniques over the years. Since we came to CEMAS, my focus has narrowed a little bit. I'm looking at mostly the TEMs, primarily the TechNIs, X-ray diffraction. I teach a couple of courses and then answer whatever questions seem to come up. Outside of OSU, I tend to do a lot of cycling. I'm a ride leader for Columbus Outdoor Pursuits. I do swimming, and at the moment, I'm helping look after my grandkids who are back in the States after being overseas, and you know, I'm trying to help keep them entertained while their parents are still trying to get some work done. So about X-ray diffraction, in 1912, Peter Awald, was trying to solve some problems in crystal structure. And he sat down with Max von Laue, and they started talking about possibly using X-rays to examine crystal structure. Well, Laue went back to his lab, and in only 2 years, he won a Nobel Prize for discovery of diffraction of X-rays by crystals. And then the following year, Sir William Henry Bragg and his son, William Lawrence Bragg, won the Nobel Prize in Physics for their services in the analysis of crystal structure. So it's now been a bit over 100 years since these people won their Nobels, and there have been a lot of people who've been doing a lot of work in doing X-ray diffraction, coming up with all sorts of sophisticated analyses and interesting and subtle techniques. Here at CEMAS, we have 2 diffractometers. We have a small benchtop unit, the Rigaku Miniflex. It's a fixed geometry. It's very easy to use. And it really shines at doing phase identification, which is, I guess, what most people think of when we talk about X-ray diffraction. But then we also have our Rigaku Smart Lab. This is, well, somebody once described it as a Swiss Army knife. It can be configured in many different ways to bring out many different types of measurements. Now, we don't have all the configurations here, but we do have quite a few. So we can usually tailor the instrument to meet whatever type of analysis needs to be done. So as we talk about different types of analysis, the question is, obviously, what can we do with it? Well, the most common thing, and what most people think about, is phase identification. Basically, what do I have in my bag of powder? And probably it's the easiest technique to start identifying things. And I've had people hand me bags of powder and say, what is it? And then I'm left on my own. And then as part of that, we can, this qualitative identification, we can also quantify the amounts of the different phases that we have. As we're looking at these crystals that are in the crystal structure that we have in the material, we can start to look at the qualities. We can look at the size of the crystals. We can look at the texture or orientation dependence of the crystals. we can often see the residual stress that we have in crystals. And when we get to thin films, we can start to look at the quality of the thin films, as well as doing the same sort of phase identification. So, and then we can push the precision of the general measurements. And if we work very, very carefully, we can start to see lattice distortions, atom locations, and vacancies, and so on within the crystal structure. Now, not quite what we can do, but we can set up the instrument in both a parallel beam and what we call the Bragg-Brentano geometry, BB geometry, which are optimal for different types of analysis. So, thinking back to your freshman physics course, you've probably heard of Young's slit experiment. So if you have light coming in on two slits, then on the back side of that, the waves coming out of these two slits in some places will interfere constructively, and in other places they will interfere destructively and cancel out. And then what you will see on a screen back here is a series of bright bands showing the constructive and the destructive interference. And as you move these slits a little closer together, you'll see that these bands move farther apart. And as you move the slits farther apart, conversely, then the bands will move closer together. Well, we're doing something similar in X-ray diffraction. The X-rays that come in have a wavelength close to that of the spacing of the atoms. And each atom will become a source of scattered radiation, like the slits. So as we look at the output, if we look at the angles coming out here, we will have constructive and destructive interference pattern showing up. So we will see bright and dark lines. Now we can simplify the situation. Since we have a crystal, we can assume these atoms are sitting on planes, and then that simplifies our calculations so that we can think of a situation like this where we have a certain spacing between the planes, we're coming in at a certain angle, and we can then derive the Bragg equation for constructive interference. So now we normally will set n equal to 1. We know what lambda is, that's our wavelength. We can measure the angle where the peak is, and that tells us the d spacing, or the spacing between the planes. And from that, then, we can get a fingerprint of the crystal structure. So we have, coming out of the machine, then, we will get something that looks like this, where this is our scattering angle, this is in 2 theta, and the intensity. So as we scan through the angle, we will see these peaks showing up. Now, the position of the peaks and angle tells us d spacings, but then also we have the intensity, which is the area under the curve. We have the peak width, and actually the shape of the peaks as well. And all those different aspects will give us information about the atomic arrangement. Now, most of what we do here at CEMAS is called powder X-ray diffraction. So the assumption here is that we have an infinite number of small crystals that are randomly oriented. So as we come in with our X-ray beam and we look at our scattered radiation, the only lattice planes that are diffracting are those that are parallel to the surface. So we're only sampling some of these lattice planes, which is why we want to have a lot of crystallites in our beam to get a reasonable representation. And then as we scan through, we'll pick up these crystals and see what they are. Now this shows a thin film, but we can also be looking at solid samples or powders as well. So we call it powder X-ray diffraction, even though some of the samples are in solid form, because we have just many different small crystallites in there that behave as though they're a powder. So if we have a crystal structure, we can consider an arrangement of atoms like this. So this is potassium chloride and potassium fluoride. So we see that we have here a nice cubic arrangement of our purple potassium atoms. And we see we have an alternating arrangement of the green chlorine atoms here. Now, the potassium fluoride, and it's a little harder to see, has the same cubic crystal structure as the potassium chloride. The difference is now that we have fluorine atoms, which are much, much smaller. Potassium and chlorine are very close to each other in the periodic table and will scatter at about the same amount. The potassium and fluorine scatter much differently, so you get a different amount of scattering from the two atoms. So if we look at the patterns that come from these two structures, we get something like this. So they have a similar kind of a structure, but in the potassium fluoride, you see that there's a peak here that is absent in the potassium chloride. And it's because we get destructive interference coming from the chlorine atoms. The potassium and chlorine destructively interfere since they're almost the same scattering power. And since the fluorine has much less scattering power, it doesn't cancel out as much as the chlorine does, and we tend to see a peak. So we can take this information of where peaks are and are not, and then we can go into our database structure, database library, which we have somewhere in the order over 400,000 entries. And we can start to compare the pattern that we see with the patterns that are stored in the library, and can then identify these phases. Now, an example of where this came up was somebody handed me a bag of soil and said, "What's in it? What kind of soil do we have?" Now, you notice I have one very strong peak here and then a whole bunch of smaller peaks. So in the next slide, I'm going to show a different y-axis. I'm going to show a square root that helps me see these smaller peaks a little more clearly. So this is a square root scale. So it's enhancing these smaller peaks while still allowing me to see the big peaks. And I made a guess. I said, well, soil tends to have a lot of silicon and oxygen in it, so let me look for silicates. And I then put that elemental constraint into the database, and it returned that I had quartz in my sample. And if I look at where the peaks are from my library, they match up very, very well with the peaks that I have in my scan. So I then went through and I looked for other possible elements and so on. And after some effort, I came up with an identification of mostly quartz, some calcium carbonate or calcite. I had kaolinite in there, which is a clay mineral, and then various other minerals, including montmorillonite, which is another clay mineral. So pulling out 6 different phases from this one data scan is actually pretty good for most materials. They're very seldom do you have this many phases in there. Now, not only can we look at all these different minerals, but sometimes when you're looking at different phases, these have the same chemical composition. Titanium dioxide, 1 titanium, 2 oxygen. But it turns out that titanium dioxide can actually crystallize 3 different ways. You can have one crystal structure, which is called anatase, another crystal structure called rutile, and then there's a third crystal structure called brookite, which is generally less common. So this particular sample, we went through, we did the analysis on it, and then we used some library sensitivity values, and we could then quantify the results. So this was almost 90% anatase, 11% rutile. Now these have the same chemical composition, but they have the different structure, and we're able to see that difference. Now, as you're working with different materials, one thing that you can run into is an issue with sample fluorescence. Fluorescence is what happens when the X-ray coming in effectively ionizes the sample. Now, X-rays are known as ionizing radiation. They are dangerous for people and other living material as well. But as we're looking here, we're ionizing the iron in this sample very well and gives us a very high background. So we have to put a monochromator in to reduce the background. And then that allows us to see our peaks much more clearly. So for example, this peak here is just barely visible in the unfiltered scan, and you miss these 3 peaks right here that are quite visible in this scan. So this is primarily a problem with the elements just below copper in the periodic table. So cobalt, iron, manganese, chrome tend to have a lot of fluorescence. So our smart lab, we do have a monochromator. We can minimize this effect. So as we're looking at crystal structures, one of the things that we find is that as we make our lattice or our crystal very, very small, our peaks get wider. So if we start looking at the number of unit cells, those cubes in the crystal, if we're down to 5 unit cells, we get a very, very wide peak, not very well defined. As we increase the number of unit cells, our crystallite size gets bigger. You see that our peak gets a little bit sharper and gets a little bit sharper as we get up to 20. And by the time we're up to about 100 unit cells, our peaks are getting pretty sharp. Now, the area under the curve is remaining the same. It's just that it's now all compressed into one angle. So we can now take this information and use it to estimate the size of the crystals that we have in our sample. So we have a certain amount of width in our peaks due to the instrument itself. That's our instrumental resolution. But once we get down to below somewhere around 200 nanometers, down into 3 to 5 nanometer range, in this range of, say, 3 to 5 up to 200 nanometers, we can use this broadening to estimate the size of the crystals. Now, going back, well, actually, the simplest way to do this is to use the Scherrer Equation, which again is a very simple way of going about it. There are more sophisticated curve fitting techniques. But this gives actually very good results. So once again, we have the wavelength of our radiation, which we know are X-rays. We know the angle of the peak. We can measure how much broader the peak is than our instrument. We need to have some sort of a standard. And then we can just very easily calculate the size of the crystal. So going back to that titanium dioxide sample that we had earlier, so not only did we calculate the amount of material, we could actually calculate the crystal size. And based on the broadening, we find that the anatase crystals came out quite a bit smaller, only 2/3 the size of the rutile crystals. So this will very much affect the properties of the crystals that you have. If you're interested in doing catalyst work, or if in the case here, this was a sunscreen, these crystals will absorb differently depending on their size. So this is an important parameter for many materials people. So not only are we able to determine the type of crystals we have and the amount and their size, the other thing we're interested in can be the orientation or the distribution of the orientations of those crystals. Now in powder X-ray diffraction, we really like to have an infinite number of randomly distributed crystals without any kind of a preferred orientation. But in many materials, as you start machining them or rolling them or doing whatever, particularly in metals, they will often take a preferred orientation. All those little crystals will align in the same direction. So you can think of squeezing pasta dough through a die. All those crystals, all those pasta strands are going to line up in the same direction. So you can think of that in a way like fibers. So we can actually measure the amount of this texturing, that we, as we call it, by doing X-ray pole figure analysis. You can do the same thing in an SEM with EBSD analysis, but the X-ray pole figures will give you an average texture over a larger area and also deeper relative to the EBSD. EBSD is very sensitive to surface damage in your material, so you're only analyzing tens of nanometers deep. whereas this can go microns to tens of microns deep. And depending on your grain size, you may actually wind up with more grains in a single measurement using the X-ray than you do in EBSD. So you may be able to get better statistics. EBSD, however, will show you the relationship between the adjacent grains, which is something that X-ray can't do. So what a pole figure does is it measures the distribution of a particular reflection in space. So remember that a reflection here is indicative of a particular crystal plane. So it's basically telling us the orientation of that crystal plane around in space. Which way is it pointing? So you're seeing, and then you normally describe that with respect to some sort of a sample reference frame. And because this has come out so often in metallurgy, it's often referred to as the rolling direction and the transverse direction. So normally now, people will use a 4 or 5 axis goniometer to measure these things. And there are some pluses and minuses to this. Our smart lab we don't actually have one of these goniometers. However, we do have an out-of-plane arm, and we can do something equivalent to the 4 or 5 axis goniometer. And I think there are actually some advantages to using this out-of-plane arm. So the idea here is that we set a particular 2 theta angle. So if you remember back our scattering, when in our scan, we had certain peaks. So we set our angles so that we're sitting right on one of the peaks, and then we can start spinning the sample around its normal and see where those peaks are relative in this part of the hemisphere, in this part of the hemisphere, and in this part. And then just work our way right up to the top of the hemisphere. So we're seeing where those planes are distributed through this hemisphere. And what you get for a single pole looks something like this. So this is some rolled copper foil, and this is the 111 plane in the crystal. So this would be the body diagonal going through the cube. And these red parts are where most of the 111 planes are pointing. Now, if I take that information, and then the rolling direction is vertical. So this tape was aligned more or less up and down with my scan. So if we take this information, and this is a slightly different contrast ratio, we can actually start and I can take a section across this pattern. So this would be slicing through the upper hemisphere, or I can take one particular latitude in that hemisphere and look at the distribution around that. So if I start doing that now, if I go 35 degrees up from the equator, I find that I've got now my 111 planes are showing every 90 degrees, I've got a lot of 111 planes. And those are my body diagonals. If I take a section through, I find a peak at about 35 degrees up, which is roughly where that plane should be in a cube, and then at about 55 degrees up. So that's what you're seeing as in this section across the hemisphere. Now we're not seeing the 220 planes, which are the diagonals through the cube here. That's this green line. You're not seeing much of a difference there. But if I move my angle now from 35 degrees up to 45 degrees now, and I look around that azimuth, every 90 degrees, I've got a 220 plane. So this is showing me the distribution of 3 different sets of planes. My 220, or one of the faces of my cube, is sitting up at 90 degrees, which would be parallel to the surface of my sample. So taking all these 3 planes now, I can start to work out and get a complete orientation distribution function. And I can express that in terms of a number of different ways. But here is one example showing what are called inverse pole figures. In the X Y, and Z directions, showing where those poles are distributed. So these are all very nicely done in the bulk, but we can also start looking at thin films in our samples. Now we can have thin films that are polycrystalline or thin films that are single crystal. So polycrystalline films would be something like rust or corrosion on a surface. And we can get essentially the same information we get from conventional X-ray diffraction, but we want to keep our scattering right within this very thin layer on the surface. And we can do that by using a parallel beam and then just scanning our detector. And we can do this, and it keeps the scattering within those top few nanometers of the sample. So very useful for these films that are sort of in the tens to a few hundred nanometer thicknesses. But we can also start to look at single crystal thin films. This would be very important for the semiconductor industry or growth type of things. And we can do conventional scanning to see the distribution. And we can do rocking curves and reciprocal space maps to look for defects in the material. But there's another measurement called X-ray reflectivity, which allows us to see the thicknesses of the layers that we've grown. So any discontinuity acts almost like a plane or a difference in scattering. So you need a very parallel beam, and you come in at a very shallow angle. And then our interference fringes will tell us the thickness of the layer, density, and we can estimate composition and roughness of the layers. So what you get, and now look at these angles here. This is from 0 up to about 6 or 7 degrees that you're seeing this. Our normal theta, 2 theta scans are usually going up to 80 or 90 degrees, 2 theta. So here, starting at 0, we are getting total external reflection of the X-ray beam. And then once the beam starts to penetrate, we start to see these oscillations in the scan. And the spacing of the oscillations tells us the film thickness. The size of the oscillations tells us the change in density. And the way that this curve drops down and the way these oscillations die out give us information about the roughness of the layers. So we have to start with a model, and then we modify the model to match our experimental data. So here is one model that we matched to a molybdenum thin film grown on silicon. So you see here we start at 0 degrees and we went out to 10 degrees. We're only looking out to about 5. So I'm going to be fitting this area in the light, and as I start fitting it, and I look at this fit, I say, you know, that really isn't very good. It sure doesn't match up very well here, and it sure doesn't match up there. What's wrong? Well, as it turns out, we neglected the oxides. When you're starting with a piece of silicon, you often have a very thin oxide on the surface. And then after they grew the molybdenum, you got a little molybdenum oxide on the surface. So once we include the oxides now, this is the way our data looks. And if we zoom in on it, you can see that our fit is much, much better. So once we include the oxides, we can come up with these numbers. So we have we chose moly dioxide as the oxide. Actually, that should be MoO3, I think. And silicon dioxide on the silicon. So this was a nominal 400 angstrom film, or 40 nanometers. And our measurement showed it came out at about 31, which in the thin film business is actually not too bad. They can now calibrate their system to come up with better thin film measurement, better depositions by using this type of a technique. Now we had another sample come in of vanadium oxide grown on alumina. And it was, the grower told us that it was 800 angstroms, or 80 nanometers thick. Well, we came through and we started modeling this and discovered that the vanadium oxide was only 26 nanometers and not 80. So it was less than a third of the actual thickness that they thought it was. So just as a word of warning to those people who have collaborators, trust but verify. It's hard to grow things exactly, and sometimes the calibrations in the growth chambers are not that great. So we fed this back to the collaborator, and I think he is adjusting his system a bit more. So now, also looking at crystal quality, our smart lab can also do rocking curves and reciprocal space maps. Now on campus, we also have some dedicated systems for doing reciprocal space maps. And while we can do it, it takes our system a little longer to get calibrated and set up, but we can actually do this quite well. And the thing to note here is that this is a log scale, and we're looking at about 5 to 6 orders of magnitude between the intensity in this peak and the intensity in these hubs. So it takes a little while to collect the data to get sufficient statistics that you get a nice film. But then this is telling you now the quality of your growth. And with that, I think I'm going to end here on talking about X-rays. And I'm going to put up our schedule for what's coming up. You can always find the schedule and recordings at this website. So next week, Jinwoo Wang will be talking about 4D STEM, and then Dan will be talking about cathodoluminescence. And we'll have a guest speaker in, Vicky Wysocki, talking about the Campus Chemical Instrumentation Center. And as always, we have many resources here. You're welcome to join in any of our webinars on Wednesday afternoons. You can email the address here if you have questions or whatever out of the webinar time. And stay connected, please. So with that, I will turn it over to Dan, and he can let us know what questions there are.